Hello, physics students. So in this video lesson, my target for this is that you can apply, define the kinetic and potential energies, and we're talking potential here, or gravitational potential energy, as well as apply the equations for each of these, and then manipulate those equations around to solve for unknown variables. This is going to lead us into the next lesson, which will be conservation of those energies, and then eventually into our pendulum, so we can actually apply this to a pendulum in order to make some predictions that we'll do in a lab. So let's start with some basic definitions. This is review for many of you, at least the definitions. The computations may be a little bit different. So and I don't necessarily need you to necessarily write these things down. I will always give you the equation, but you are going to want to have pencil and paper available to help solve some of the problems a little bit later in the quizzes. So gravitational energy is simply what's stored energy. And when we think of kinetic, this is energy that's being released or energy that's in motion. And we are talking gravitational potential energy here because we are thinking about moving away from the center of the Earth. So the energy is really being stored in that object. So if we release it, it will want to fall back to Earth. There are other kinds of potential energy. If I have a watch and it's a wind-up watch, like an old-fashioned watch, when I wind that up, I'm coiling up some springs, which are storing that mechanical energy. That would be kind of a stored potential mechanical energy. Batteries are a form of stored chemical energy in which that can be used to do work. You could say kinetic energy then is the actual moving of the watch parts or the actual releasing of those electrons in a battery in order to make the watch work. If we think of a solar powered calculator, then you're taking the energy from the sun, it's going into the calculator, and then that energy is then being used to do the work. But in this case, we're really talking about gravitational. So we're talking about opposing gravity. So we're lifting something up, and then gravity is pushing it back down. And in fact, we think of gravity actually pushes, it doesn't pull, which is kind of a weird thing to think about. We'll get to that a little bit later. It is important to say that for our purposes, we are going to, unless you're told otherwise, which you will be told otherwise here in a few minutes, when we're working in the lab, we will want to use 9.81 meters per second squared, okay? For today's purposes, for this activity that we're doing today, I want you to go ahead and I want you to round that off to 10.0 meters per second squared, just for today. We don't necessarily need to get a bunch of decimals today, so I want to make it a little easier. So for today, and unless you're told, but once we're working in the lab, then we'll use 9.81 because we can measure things a little more precisely. Now, basic equation. We really need to know three things to calculate the gravitational potential energy. Well, we need to know the mass of an object, and that kind of makes sense because if I take this pencil and I lift it up, and I take this stapler and pick it up, I'm actually giving the stapler more energy. It took more work for me to actually lift this up. It has a greater mass. If I drop this, it's going to hit the ground with a greater amount of energy, so to speak. I could do more damage dropping this on my foot than I would dropping this on my foot. So it is important to know the mass of the object that we're doing, and we're always going to measure this in kilograms for our purposes. Gravity, so we need to know the value of gravity. So I've said for our purposes today, we'll use the number of 10, and we will not let that limit our sig fig, so we'll say it's 10.000 forever. We're just rounding it off to exactly 10 today. And then we need to know the height, and that height will also be measured in meters. Since we're working in meters here with gravity, we also want to work in meters with our height. So how do we get those units? And so we have a unit that's called a joule, but how does that work out? Well, let me show you like unit analysis. Okay, so gravitational, potential energy. Oh, that's messy. Potential energy, PE. Okay, so I'm going to do something what I call my railroad tracks. And so this is really nice if we're just doing multiplication division. So I'm going to be taking mass. So mass is in kilograms. That's my first unit. And then if I do a bar up and down, that just means multiply. So it's like putting parentheses around it here. And then I'm going to be doing gravity. So gravity is meters. The line horizontally is the per line. That's the dividing line in a fraction. So meters per second squared could be written like that. So this is my per second squared, okay? And then I'm going to be multiplying by height. And I said my height I want to do in meters. So if I multiply these numbers out, I'm going to get kilogram meter squared. So meter times meter will be meter squared. So I've got my kilogram meter squared per, that's second squared on the bottom. That unit, and this should actually be in kg, sorry. So this unit is a joule. It's a derived unit. When I say derived, we're using the equation to come up with that unit. Joule was a scientist who did energy and worked with some things back in the day. Now, potential energy, I said that's the energy released or the energy in motion. So motion makes us think velocity. And that's the important part here. This doesn't really necessarily have to do with gravity. This is in motion. Now, we are also measuring joules, which would mean we should have the same units. Now, let's see if that works out. So if I take my kinetic energy, okay, I'm going to do my equation again. So I'm going to be taking now this time, okay, there's a 1/2 in here, and it makes that coefficient makes it like a in our, so when you're doing, and since this is squared, it's actually, it's a curved line, so a is sort of that. If you remember doing when you did parabolas, it was always ax squared. It's that number that's in the front. So this is the coefficient that's in front, makes the math kind of work out. Mass, kilograms. Now, I'm doing velocity squared. So I'm going to do meters per second. Now, if I square this, if I take meter per second and I square this, we actually saw this when we did our pendulum period. If we square this, both units, both the top and bottom, must get squared. So if I take this and I square it, so it's like taking that times meter per second again. And if I work that out, I get kilogram. There, I did it again. So kilogram, m times m, meter squared, divided by, that's my dividing line, second times second is second squared. So the units are identical. They work out exactly the same way. So these derived units of joules work for both kinetic energy and potential energy. So let's put that into action. So I'm going to talk about gravitational potential energy first. So in my gravitational potential energy, so I have a hill set up here, and we're going to measure it. Let's suppose this is height of 0. So this is our 0. So potential energy, we don't necessarily, because if we dropped an object, it would hit the ground and stop. It wouldn't keep going to the center of the Earth. And so we're kind of measuring it from the bottom of wherever our ground is, or wherever the bottom of the object it could possibly reach. When we get to the pendulum, it's going to be the bottom of the pit of the swing. That's a little bit later. So let's take our purpose here. So we've got this ball that's set up, this bowling ball or whatever it might be, and we're going to ignore friction for this. We are ignoring friction for now. So we've got this object that I've down here at the bottom. What would be its potential energy down here at the bottom of the hill? Well, it would be 0 here because it's at the bottom of the hill. It can't go down any further. So I've picked that object up. I've carried it up this hill, which is a really steep hill, by the way. And I've carried it up here a total height of 5 meters. So this would be like you climbing up. So our stairs, our stairs are about, if you go from the 2nd floor to the 3rd floor, you increased your potential energy by about 5 meters. We could actually calculate how much work you did from that. So when I got to the top of this hill, I carried this bowling ball that was 3 kilograms. That's about 7-ish pounds up this hill. How much potential energy did I add to this ball? And I'm saying add because it technically had some here because it was, siren, sorry about that. So what did I add to this? So I want to, if I'm figuring out how much GPE did the ball have at the top of the hill, so I'm going to apply this equation. So my GPE, and I apologize that I can't write very neatly here, Now, I like to just start my big railroad track like this. And so what I'm going to do is I'm going to take the mass, so my mass of 3. Now, I'm going to write it like this and knowing that we have 2 sig figs here. So, well, I'll try. Okay, so 3.0 kilograms. And I should have, tell you what, let me start over here. That's not a very nice job. Okay, so here's my PE. Okay, so my mass, I've got 3.0 kilograms. Now, my bar up here, because I'm going to go to my next unit. Gravity, so remember for our use, what did I say we're going to use? We're going to use 10.0 meters per second squared times my height. What's my height here? It's 5.0 meters. 5.0 meters. So when I multiply this out, meters times meters, meters squared divided by second squared times my kilograms, that's our joule. So we're just going to write that as joules. We don't necessarily need to write out the derived units. So now I can multiply 3 times 10, 30, times 5, 150. Now this is a wonky example because of our sig figs. So I kind of double cross this here a little bit when we're reporting it. So 3.0 kilograms has 2 sig figs. This has 2 sig figs. Our final answer should have 2 sig figs. Oh, I didn't double cross this at all. We're good. 150 joules, and we are good. So this is the amount of energy that I added to that ball. Okay, pretty straightforward if we're figuring out the potential energy. Now, let's do a case now. So I've changed it a little bit here. So in this example, I'm given the mass, I don't know height, but let's suppose, and I should have written in here, and I apologize. Let's suppose that I'm telling you the potential energy. Now I'm not going to have worked it, so we're probably going to get an ugly number. Let's suppose that I give you that we have 260 joules of energy measured up here. I want us to figure out what the height is. So I want us to figure out what height is. So this time we don't know height. So what are we going to have to do here? Well, we're going to have to solve for h. So when I manipulate this around, if I solve for h, I hope you see pretty quickly. And so I'm going to do PE, kind of keep that together, equals. Now, what am I going to do here? Well, I'm going to divide both the top and bottom by mg. So if I divide by mg, that should equal my height. So we've just manipulated that equation around to solve for that. So let's go ahead and do this. So let's take our let's plug things in. So we got 260. Now, what were my joules? My joules were kilogram. If I do my units out right, I want to show you how this works. Meters squared divided by, I'm going to build a big long railroad track here, by second squared. Okay, now divided by mass. My mass, in this case, I was told it's 5.0 kilograms, 5.0 kilograms. Now I'm going to do another bar here. So I've got my potential energy in here. Now notice it takes up a whole part of my railroad track here because I had to put my second square in the bottom. Got my mass now taken care of. Now gravity. So gravity, I said for our purpose, we're going to do 10.0 meter. Now this is a tricky part here. So when we say per second squared, it actually flips up here onto the top. Per second squared equals my height. Now we know height should be measured in meters. So let's see what happened to our units here. These kilograms cross off with those kilograms. These meters squared here, oops, I can't undo just one thing, that's unfortunate. One of my units, so my squared cancels out with this left, and we actually are left with 1 meter. So not 1 meter, but the unit of meters. My second squared here, go out with second squared here, and I'm left with 1 lone unit of 1 of my meters. Now, do the math. So I'm going to do 260, and this is, yep, I didn't pick a very good number. 5 times 10 is 50. So whatever this equals, I'm going to have to come down here and grab a calculator because it's too dark in my room here to this actually work. So I have a calculator here. You have to trust me. I'm going to do this out. So 260 divided by my 50 equals 5.2. So let me grab my pen tool back here. And now, how many sig figs? So I have 2 sig figs here. I had 2 sig figs in here, so I can actually report 2 sig figs. This works out to 5.2 meters. Now, how did I know that it was meters? Because I had this 1 meter left over, but I knew I was solving for height. I did my equation right. Works out. Now, I could also solve this for G. I could be on some planet that I don't know the gravity of, and then I could solve for G here. I could solve for mass here if I wanted to. It'd just be a matter of manipulating my equation the way I needed to. All right, so hopefully GPE and PE, you kind of got that down, or excuse me, the gravitational potential energy here. I haven't worked any of the kinetic energy. So what I'm going to ask you to do now is this video is going to stop. It's going to end. I want you to go to the next slide and work these potential energy problems that I'm posing to you. Do your best. Now, it'll be fill in the blank. So make sure that you're just reporting the proper number of sig figs. Remember, our gravity we're going to use is 10.0 meters per second squared. And so report the numbers in the correct number of sig figs here. I will also then, you'll be able to see the right answer. If you need to go back to try to figure out why you would have missed something, let me know. I'm probably not going to put an answer key with these today. I think if you have problems, I know that one student will be working at home. So if that student, if this is the year 2021 that I'm making this one, if I'm using it in another year, then who knows what's going on. So do your best. And then I will be back in a few minutes with kinetic energy problems. So, all right. Thanks for watching so far. All right, so now I'm here to talk about kinetic energy. So hopefully you were successful in doing your potential energy problems. So in kinetic energy now, we're worried about motion. We don't need to worry about gravity anymore. We're just, this object is in motion now. And you know, our base equation here that we had, kinetic energy is 1/2 mv squared. So there's our equation we're using. Probably see where I'm going now. We're gonna solve some kinetic energy problems, and then I'm gonna ask you to solve for some other variables as well. So we have a ball that has a mass of 3 kilograms. So here we go with 3 kilograms. It's moving at a velocity of 6 meters per second. What's the KE? So I just want to show you how I would apply it in the way that I actually plug things in. So I'm going to go ahead and do myself a big long railroad track here. And I know that I just need to plug things into this. So I'm going to do my 1/2. So I'm going to literally so this line here represents my dividing line. Mass. So my mass, 3.0 kilograms. Okay. V squared. So I've got my velocity of 6. So 6.0 meters per second. And all of that gets squared. So remember, it's going to be meter squared, second squared. That makes our units work out. So if I do the problem here, and again, I haven't worked these ahead. So 3 times, let's see, 6 times 6 is 36. 36 times 3, 36. And I'm working that over here on the side on my calculator. So that's why so I get 108 there. So I have 108, and I need to divide that by 2. So divided by 2. And if I work this out, then I actually find that my KE, which is really sloppy. Again, I apologize. I'm trying to write with a mouse, is equal to 54 joules. Now, sig figs wise, 2 sig figs here, 2 sig figs here. So I can report that as 54 joules. Okay, makes sense? The application of that is just algebra, right? We're just plugging things in and solving for that. Okay, so potential energy, as long as you've got the equation there, you know, you're just plugging things in, make sure you're using kilograms, and then make sure when we do our velocity, we're using meters per second squared. Okay, so next, got one where we don't know everything. So in this case, I'm telling you that the ball has 45 joules. We've changed the mass this time. It's a little lighter to 2 kilograms. And now this time, we're solving for the velocity. So I need to get velocity by itself. So if I get velocity by itself, let's see, what should we do first? Well, let's write things out here. So KE, because again, I will expect you to be able to do this because of, I'll just give you the base equation. So mv squared. So the first thing I'm going to do is I'm going to multiply both sides by 2. So if I multiply both sides by 2, and this would go off with this. Okay, that makes sense. So now so now I'm going to clean this up a little bit with my, I don't want to do that. There used to be a way that I could just do my eraser. And so this, I'm going to clean this up a little bit because that went away and this goes away. So now I've got 2 KE, 2 times kinetic energy is mv squared. Now I can divide by m. Okay, so now I'm gonna clean that up a little bit. So I'm gonna grab my eraser tool here, and so my masses will now cancel out. So now I've got all of this, 2mv over mass, can now do square root. Okay, and once I do my square root, then we've got ourselves a new derived unit. This squared root, we'll take that out, and there we have it. So this one's a little goofier, and in fact, we've got 2 times KE divided by mass, square root that will give us our velocity. So let's plug this in and see what we get for this. Again, it's going to be probably a wonky number just because I made up the numbers and they're real numbers. So I know when I set this time up, and I might kind of cheat a little bit here. I'm gonna draw a big. I know all this needs to be under the square root. Okay, so I've got the number 2 times my kinetic energy. What's my kinetic energy? 45. So 45. Now I want to just show you so that you know how the units work out. I know that's meters. Oops, Mr. Accurate. That's not a very good job. So I forgot my kilograms. So 45 kilogram meter squared per second squared, okay, divided by mass. And so my mass, I'm told, is 2. So 2.0 kilograms. So I want to show you what happens here. These kilograms go along with that kilogram. Now, when I have meters squared per second squared, if I take the square root of that, well, I'm getting rid of the squared. So I'm left with meters per second, which is what we want with velocity. So when I plug this in, so I'm going to come over to my calculator and plug this in. So I'll give you a play-by-play. So I'm taking 2 times 45, which should give me 90, divided by 2, which gives me 45. So in this case, now it isn't always going to work out like this, but because I did 2 KE and then I actually made the mass 2, this 2 and this 2 actually cancel out. It's not always going to be like that now. It's just kind of dumb luck. So if I have 45 now, so I've in my calculator, you have to trust me here. I've got the number 45. I need to square root that. So if I take the square root of 45, I'm going to get, so all this is my velocity. So my velocity equals 6.708203923249939. I'm not going to write all that down. Because I had 2 sig figs here, I've got 2 here. We should report our answer to 2. So 6.7 is what it rounded to. And you must put a unit on there, meter per second. Okay, so this equation is a little wonky just because it's got the square root in there, but you can see how I worked this out. And hopefully that kind of makes sense. So now I'm going to give you a series of questions in which I'll ask you to then solve for the unknown variable in these kinetic energy problems. And that'll be the end of this lesson. So that's just, and I'll ask you some definition questions of things real quickly, and then I'll ask you to rate your mastery of your ability to do these. So thanks for watching. Continue on now to the practice problems.